All right. So I already have my screen shared here. Oh, before I go into office hour questions, I did want to point out one last thing. This project right here, so if you are, give me a thumbs up if you're in section 18 right now. Okay. Has anyone started this project regression modeling by chance? So I see some head shakes. Okay. So some quick things is that we are updating this project in particular. Mostly, to be quite honest, is because of the Boston housing data set. There are some, how do I put this? There are some issues with the Boston housing data set that it's honestly, if lack of a better word, kind of racist. Basically, there's some information in there that like isn't really a great use. Like I've talked about like bad data going in, bad results coming out. Boston housing data set could be arguably said it's bad data because there's some issues with like how the data was collected and all these different things. So we've been trying to, like the curriculum team has been trying to work on like trying to find a data set that is comparable to the Boston housing data set, but it's more relevant in the sense that like it's a good data set, so you can kind of deal with that. So they're in the process right now of using the Ames data set and updating this lesson. So the thing is though, and I was talking to the curriculum team literally earlier today, is that the idea is that we deploy this out and so to replace this lesson, but that means if you start working on this and then you go to check back on, you know, like go onto this link and check out like the solution set, right? So like you would check out the solution, that solution wouldn't be there anymore. It wouldn't be for this particular data set. So I'm just letting you guys know right now is that if you get to this point right here, like honestly, just message me, say, hey, I'm at the project part right here. I'm planning to do this, you know, what do I need to know about updates? And I'm going to see if I can get at least like a draft. And so I can tell you, okay, this is what you should do. Like, I think literally it might just be like trying to change out the data set on how you load it. That way you guys are working on something, the code itself, like the code solution will be relevant to you. And I think I saw Nadine raise her hand.
Yeah, sorry, is there a way we could like download the solution and it, because it is like a really popular data set to practice on.
Yeah.
So is there a way if we were to sort of like save the solution now?
You're talking about like this stuff, like it right now, right? Yeah. So if you just go to the GitHub repo, right, that's connected on here, you go to here, so you'll see this is the repo. If you go ahead and just like, you can either clone or download, you can just download the zip.
The whole thing, yeah.
And then you can also switch over to solution and do the same thing and do that. Download the branch. Make sense?
Thanks, yeah.
Yeah, okay, cool. You can also do like a git clone, like, you know, like using git bash, but know that you also have to do, you have to make sure you download the solution branch, not just the master. So just kind of be aware of that. And if you need help with that, let me know. But it's kind of good practice too, to know how to like make sure you basically get that other branch. It's fun fact is that if you do a git clone, you should actually have all of the branches that are available on here. I think there's only 2 that you guys will see. I think this one's a private branch. I could be wrong, but no, I'm wrong. But there could be 2 to 3 branches on there. It should actually get all of those things, but you won't see them by default when you do like git branch and see like all the branches on there. So I think the easier thing probably for where you guys are right now is just probably download the .zip. Okay. Good question. And note that this is the one that's most immediate. I think there's maybe 1 or 2 other lessons in here that might have the Boston housing data set. Okay. And note that those will also be updated too. Note that the URL that this points to might not be called, like even though it says DSC regression Boston lab, it'll still be called Boston lab, but the data set will be updated. Okay. Cool. Any questions? Any other questions on that? All right, cool. All right, I wanted to point that out before I forget. So question time. All right. So questions. I know this was asked last time right here with this lab, and just because I don't have the lesson in particular, I did come across this. Did the person who asked this, are they here today? Like, sure. Andy, do you know what lesson this was by chance? I remember seeing it before, but. Let's see here, section 18.
It's like the 3rd one in there.
It's a simple regression lab. Simple linear regression.
Yeah. Okay, cool. Yeah. So this basically, this equation, while this loads for a second, this equation basically is relating to essentially like covariance. And so I know it's kind of confusing. You're like, well, this x bar, y bar, and then this x times y bar. And basically what's happening here, let's see if I can pull this up. There we go. So it basically is coming from this guy right here. And rho in this case is not a p, it's technically rho. It's the correlation coefficient, and sx and xy are like standard deviations. And so what they basically have together is doing, you can simplify this into this form. So just a reminder that the standard deviation here, let's see, where's my annotation tool? Here, I'll just write it on here since we're, oops, no, that's fine. Okay, so S of like Y is the standard deviation, right? So what that's going to look like is just going to be like sigma, right? But that's going to be, or I'm going to just put like square root of this, square root of sigma squared. That can just simply be, if we write remember the equation for how we calculate variance. It's got this summation. We have y minus y bar, so the mean, squared all over. And good job. All right. And then I shouldn't put y hat. This is like I. So like this is each data point. Okay. So that's how you find the standard deviation from here, or the variance on this guy. And so basically you can take this equation, put it over here, and actually simplify it out. And the reason why you're seeing this x and y is because this is just the y's parts in here. And so you can simplify it into this point. And they're just basically saying like, well, what's this mean right here? Well, x bar, it's just saying the sum of all x's, x of I, if I'm being precise, divided by n. So xy bar is going to be the sum of x times y for each of those parts all over n. And these are pairs, right? So like you can imagine a graph, like this x belongs with this y, so you can pair them up in that way. And so that's why we get this x bar, right? Xy bar. And then anyone got a guess if I do x, if I have, you'll see that there's x bar squared, and then there's also x squared bar. So the bar is over the x squared part. Anyone got a guess of how we would write that equation? It's very similar to these two, but I'm gonna take a shot. So I'll give you a hint first, right? It's definitely a sum.
Just x, x times x over n.
Yeah, x times x or x squared, right? So x times x, and this is going to be for each x, I over n. So that's what we mean by this bar. And so this is a common notation because it's like easier to write than this guy. If you took all his information, figured out this part, if you remember Pearson's correlation, or I should say the correlation coefficient between x and y, so if you're correlating between the two, and you plug that all in, do a whole bunch of algebra, play around with it, you will eventually get to this equation down here. Okay, that makes sense? Yeah. I'm guessing, like, I mean, well, you guys probably don't want me to do a bunch of algebra just to like show you guys how this works. I trust that you guys know how to do that, right? Yeah. All right, see some nods. If you do have other questions, you know, share on Slack, or, you know, and we can maybe have like derivation. Also, you could probably look it up. I don't know how you would look this up specifically, but you could probably look up the derivation for this actual slope, m caret, or m hat. Okay, cool. Does that make sense to everyone? Any questions? Any follow-up questions on this? Okay, and again, just a reworking of the numbers. All right, cool. And then we have another question here. This is new, I haven't seen yet. Coefficient of determination. When talking about r squared as some percentage of the variation independent variable y are explained in the independent variable in our model. What does explained mean? Is that data on the model, or is the data on or close to the model? What should we understand to be close? Okay, so this is actually something we'll talk about as we get in. We're going to kind of introduce linear regression a little bit and talk about the different parts. But I'll kind of quickly say is that when you see this r squared, I'm trying to get my annotation tool. It keeps disappearing for some reason. right? If you're talking about R squared, and so like you can see here in the definitions, like is some percentage of the variations of y are explained by the independent variable. So the idea here is that this R squared is saying what percent of the variations is explained by the model. And by a model, if you remember back like when we talked about ANOVA last time, and what the model is just a line, right? And that's what linear regression really is. It's basically it's a line and saying, all right, if we have a line, how well does this line explain the actual data on here? And the way we kind of say is like, well, is this a good model or is it a bad model? Basically we say, okay, is the variation, like the variation between this, so we'll draw kind of like, usually you'll see like remember this is the model right here. We'll draw the model, the line on top of the data and say, does this model right here explain most of the variation? So is the variation within, like, do we see, for example, like if my line's like this, it's not explaining much of the variation. But if I see a model that looks like this, where we have data points, you know, more or less scattered about it evenly, we would say, oh yeah, you know, it's explaining most of the variation, but there's some of this part, like, you know, why is this point, you know, so much further up from the model? There's some variation that we didn't account for, right? Ways we can do this basically is like, maybe there's some other factor. For example, if you had like, if you want to explain, let's say, I'm trying to think something real quick. Oh, like weight. Let's say you have like weight, right? And then like the height, right? And so in general, as people get taller, right, they tend to weigh more, right? That's a general rule. But you can probably guess there's certain situations. So our model might look something like this, where as we get taller, you know, people weigh more. But you can think of situations where someone's like, you know, let's say 6 feet tall or something like that. Is that, well, some people are going to be weighing less than this model and some people are going to be weighing more of this model. What are those factors? Well, maybe there's other factors, for example, you know, type of diet, you know, maybe if we knew what kind of diet they were doing, we know the weight. Maybe if they know, well, we know some other genetic factors, maybe there's some issues like that. Maybe even using like how much income, you know, they taken per, you know, year or something like that could actually be another factor that we could use to better explain this model. So R squared here is really just saying, hey, like, how much does this line here do a good job in predicting the actual values? And so we can say, like, you know, talk about this 90%, you know, like if you have a 0.9, it explains 90% of the variance and stuff. And we can talk about like, you know, how we formalize this. We actually have an equation for R squared. But let's see here. Does that make sense for like this first question? What does explained mean? Give me a thumbs up if that's making sense. Like explain basically saying, oh, the model is fitting along this line. If we had data points directly on this line, then we explain all variance. All variance in the model is explained, or all variance in the data is explained with this model. Okay. And then is the data on the model? Or is that data on the model? I think what the interpretation of this is saying is the data, I'm trying to think. I think they're saying, are the data directly on this line?
Oh yeah, I meant like on the line.
Oh, yeah. Okay, yeah, and that's where like R squared, if it was 1.0, it would definitely be on the line. And note that even though I have this straight line here, it doesn't have to be a straight line. It could actually be, you know, like my model could be something like this, like almost like a connect the dot deal. Like it could be something along those lines. And so in general, the higher the R squared, the more closely your model's line is on top of the data. In reality, you'll never get there. But usually we use like, you should really think of the model like this and the data separately, like over here, and saying, does this model explain that data well? And so I would say like the data is not actually on the model, but the data tends to be very close. If we do a good job, our data should be close on the model's line. Does that make sense?
And if all of your dots are on the line,
Yeah.
well, then
that's a different story.
That's a whole problem, right? Then we probably
Yeah.
got overfitting that we're dealing with.
Exactly, and that's going to be the next thing too. It's like, well, a better R squared does not necessarily mean a better model. It just means that the model explains most of the variance, but you might be cheating essentially. Like essentially, you might be over-explaining it, where really you don't have that knowledge. It's kind of like if you flip a coin 3 times and it's heads every single time, it's like, and you say, your model says, oh, like it's heads every single time. Well, you guys know how coins work. If you flip that coin another 10 times, you probably won't get all heads, right? So it's over, like Avero said, like overfitting. We're being overconfident with our model, and it's going to fit perfectly on the data until we look at not data. So we'll talk about that also, I think, next time too. We're going to talk about linear regression a lot. And then let's see, or is the data close on the model? So yeah, kind of same thing, right? So close to it, and what should we understand close to be? Yeah, close is really subjective in that way. Like, what exactly does that mean? This is where we will do like normalizations and different standardization to make those values much more related to the data itself. Because if I said, oh, it's off by 1,000, you'd be like, oh my gosh, like this data point, like over here, let's just pretend it's off by 1,000. Like, oh my gosh, that's crazy. But if I tell you the overall scale of this is like 10 million, like this is like talking about $10 million and stuff like that, you're like, oh, 1,000 is like nothing. Like that's pretty much spot on. Like I couldn't ask for better results. So close is basically usually dependent on the actual data. And what's nice is that if you visually show this, you get to kind of visually see like how close the data is to the actual model. And note too, if things are normally distributed across this model, you would expect some outliers, like, well, I shouldn't say outliers, but like you'd expect some more extreme values on either end of the model. And so this is what I tell people is like, anytime you see a model that's almost too perfect, it should make you suspicious because it's probably not a good model in that case. It looks good on paper, but it's actually not a great model.
Can I just ask, is there a sort of value of R squared to aim for, or that would like determine a good or bad, or is it very like data dependent, subject dependent?
Yeah, I think that's a good point. I will tell you, people will say things like you should never have a model that has an R squared less than like 0.85 or 0.9. I don't subscribe to those theories. I think that it's going to be dependent on the data. It's going to depend on what happens. So a better thing, in my opinion, is using a baseline. How well do other models, do in predicting this stuff? And those other models could literally be, how well does someone decide on these factors? Like you have a person making these decisions, and how well do they do on getting a good result? And if you can get better than that baseline, that's going to be a better result. But shooting for a specific 0.9, 0.8, all that stuff. In general, though, I think if you have something less than 0.7, most people will be like, that's not really that great. Like that's not the best model. And I think most places would at the very least look for 0.8 or 0.85. But that's a general rule of thumb. It just really depends on your baseline itself. And also, real quick, R squared is flawed. You can cheat basically on getting better results on R squared, kind of like p hacking. And just because you have a better R squared value doesn't mean it's a better model. Okay, and then I think I saw Jessica raise her hand.
Yeah, I was just gonna say, so it's like conceptually, it's like the line or the equation that's best describing the relationship with the minimum amount of variance.
Yeah, you're saying like, how do we, could you maybe?
I wasn't asking, I guess I was just saying like, in reading the questions here you've already answered it pretty well, but in reading this, it's like conceptually, it's like, there's a relationship, potentially a relationship between X and Y. And so we're looking at all the points and then we're fitting some kind of line that's an equation that describes that relationship with an element of predictability. And it does that by minimizing the variance between each individual point of the relationship and the line.
Yeah,
so I don't know,
yeah, perfect. No, that was good. Sorry, I caught myself like listening to you, and then I was like, wait, is that right? Or like, but that was exactly it. Is that essentially like I will put caveats to each of those like little asterisks. One is that it doesn't have to be a line. So one way we do this is linear regression. We are using, in this case, we're using R squared to kind of measure that variance. But there's actual other ways too we can decide if it's a better model. But in general, the idea of the variance is how we tend to go towards it. A better way we talk about instead of R squared is actually MSE. So have you guys seen this already in the curriculum, MSE? And that's the mean square error.
Square error, yeah.
Exactly, yeah. And that's going to be that's actually calculated within, like that's folded within R squared itself in the calculation. But in the end, like you said, it's about the variance, about like how does it vary across this model. Great. Yeah, these look at that. We don't even talk about linear regression anymore. You guys basically talked about the whole key parts. No, but seriously, is there any other last questions before we move on, and we'll kind of introduce linear regression? No? All right, sound pretty good? Cool.